is Chris Nielsen. This is a webinar of the Harvard China Project on energy, economy, and environment. Start with a few logistical things before I introduce our speaker. Please keep your microphones on mute. We will have a Q&A at the end when you will be able to ask questions. You use the raise hand function in Zoom to do that. You can find that in one of the little icons at the bottom. I think it depends a little bit on which version of Zoom you're running. If you have any issues during the talk, you can post a note in the chat box, and we have somebody who will be able to respond to that. This talk is being recorded, so keep that in mind. And I want to mention that we have another talk scheduled for 3 weeks from today on April 7th at the same time. It's also a Wednesday. It'll be at 10 o'clock, and that will be by Professor Li Zheng, who is at Tsinghua University. He's a thermal engineer originally, but he's helping to run the Institute for Climate Change and Sustainable Development. I think he's going to talk about carbon neutrality in China. Okay, so our speaker today is Professor Yang Qing. She is a professor in the Department of New Energy Science and Engineering in the School of Energy and Power Engineering at Huazhong University of Science and Technology, which is one of the top universities for science and technology in China. She got her PhD at Peking University. She is a 3-year alumna of the Harvard China Project as a visiting scholar, and she's a continuing collaborator of ours. So she gave me a long description of her background for introduction purposes, and I'm going to pick just a few things out of this to give you a sense of the various things that she's involved in. She specializes in energy policy based on systems accounting for renewable energy and carbon capture and sequestration. She's involved in the assessment of non-renewable energy consumption, pollutant emissions, greenhouse gas emissions from renewable energy and CCS technologies at global, national, city, and plant scales. She's also very much involved in experimental research on the mechanisms of biomass, advanced thermal conversion technologies, such as biomass torrefaction and pyrolysis. She's going to be talking about pyrolysis today. And involved in developing new generations of catalysts, reactors, and computational models that are essential for understanding, controlling, and optimizing the chemical transformation of biomass to fuels and chemicals. A number of these technologies are moving rapidly towards commercialization. She's going to give a talk today on a very complex and study with a lot of technical dimensions. It is forthcoming in Nature Communications, but she's going to try and present this in a way that is accessible to people who are not necessarily steeped in the technical and scientific background. Those of you who are from those backgrounds and want to know all the various assumptions and details, you'll be able to get this paper in probably a couple of weeks, and if not sooner, and you can unpack it that way. But by all means, in the Q&A, you can ask any question you want on technical details and so forth. Okay, Yang Qing.
Okay, is that okay? Can you see the slides?
Yes.
Okay, thank you, Chris. Thank you for inviting me to introduce our recent work on biomass-based negative emission technologies, and thank all the participants for your time. The honor is mine. And as we all know, our human society is now facing the big challenge of climate change. Actions of China, the #1 carbon emitter, can be decisive. With many policies to reduce carbon emissions, for example, the pledge to realize carbon peak before 2030, and most importantly, to achieve carbon neutrality before 2060, we are now standing in a very critical point. China is now about to make its next 5-year plan and to make a detailed plan on how to realize carbon neutrality before 2060. So today we focus on a ready to implement carbon negative option to help China achieve carbon neutrality, biochar with biofuels. As Chris said, this presentation is mainly based on our forthcoming article in Nature Communications. And recently, many papers and also IPCC reports indicate that negative emission technologies are essential for carbon neutrality to meet 2 degrees Celsius climate change scenarios and to offset knock-in emissions before 2050. This picture shows 4 possible emission pathways leading to the achievement of a 2 degrees Celsius warming target. The orange color is BCS, BCS, short for biomass energy combined with carbon capture and storage. I have to remind you to remember this one because I will use this term a lot. And the red color is DAC, DAC, direct air capture. Both are important net emission technologies. We can see that the goal of decarbonization would be rapidly achieved, and with the exception of scenario B, backup technology are needed. And if we compare figure A and figure D, we can find that early development of backups also could reduce the risk of overshooting international carbon goals and minimize negative climate-related effects. Okay. Wait, is that okay now? I don't know why the connection is just
We can hear you.
Yeah, we got you back now. Thank you.
Okay, I'm sorry. And as we can see from this picture, there are many kinds of negative emission technologies which can be classified as photosynthesis or chemistry-based. Most of them are under development and not mature for the market. Some of them have limited potential. For example, afforestation, for which the available land resource is limited. Some will require extra energy to process. For example, the direct air capture using suspended amines. Amongst all these nets, biochar and biochar are the only ones that could provide energy to society while also capture carbon emissions. As we can see from the table, biochar is the only option that do not need energy input, but instead provide energy, and also its potentials are relatively large. However, prior literature has not evaluated another important biomass-based negative emission technology, biochar. But criteria in this table also, in many important reports, biochar and biochar are considered the key technology for reaching our carbon neutrality target. Biochar and biochar are both based on biomass. China, a highly agricultural country, is endowed with abundance of biomass resources, producing 5.5 billion tons per year. Most of these are agricultural wastes, for example, straw and crop wastes. There are 2 kinds of ways converting biomass into energy, biochemical and thermochemical conversion. The latter includes combustion gasification, and pyrolysis, all involving rapid decomposition, high conversion efficiency, and diverse product types. Biogas could require construction of CCS facilities after combustion or gasification to capture CO2, transport it by pipelines, and then inject into suitable geographical formations. It will take years to retrofit facilities and to build this CCS infrastructure requiring major equipment investments and also maintenance cost that has proven high so far. There are only a couple of biogas pilot plants in the world, and the technology is not expected to be mature in near future. Pyrolysis is another important mechanism to convert biomass into energy and fuels. It is the thermochemical decomposition of organic material at elevated temperatures in the absence of oxygen. Because no oxygen is present, the material does not combust, but the chemical compounds, for example, the cellulose, hemicellulose, and lignin that make up the materials thermally decompose into combustible gases and biochar. Some of the combustible gases can be condensed into combustible liquid. We call it pyrolysis oil or bio-oil. So, as in the figure left, the carbon in biomass is taken from the air. If we return the solid product from pyrolysis, biochar, into soil, about 70% of the carbon in biochar will be stably stored in the soil for about 100 years to realize carbon negativity. The process is very easy and cheap. We crush biochar and mix with fertilizer, then return it to soil, serving as both the medium for carbon storage and a beneficial amendment to soils. There are lots of studies showing that returning biochar into soil could increase crop productivity, hinder soil erosion, improve soil water retention capacity, and so on. Noting that biomass pyrolysis also produces bio-oil and biogas. And John Lemon said, this is the only way to make a fuel that is actually carbon negative. Studies also show that compared to biogas, biochar has better economic benefits. For example, the avoidance of costly CCS facilities, environmental benefits including benefits to soil, for example, increased soil water balance, decreased soil nitrous oxide release, and a wide range of available operational scales. But while 32 papers focused on biogas as shown in the figure, on the cost, the potentials, only 2 papers on biochar. And especially in China, despite a great deal of experimental research and recent commercial applications in China, a comprehensive assessment of biochar potential and its greenhouse gas emission reduction potential, it is not yet available. And there's also no specific policy to develop and deploy biochar technology in China. Thus, to fill this gap, we focus on the biochar technology. And also remember, the biomass pyrolysis not only can produce biochar, but also 2 other final products, pyrolysis gas and liquid fuels. The proportion of these 3 products depending on several factors, including the composition of the feedstock, and more importantly, the process parameters. you will need a temperature. And depend on the reaction time and temperature, there are three main types of biomass pyrolysis: fast, intermediate, and slow. The main product of fast pyrolysis is liquid bio oil, which is now a promising way to produce jet fuel. Biochar usually comes from slow pyrolysis with lower temperature and longer reaction time. This is an old technology. People used to use it to provide heat during winter or barbecue charcoal. Biochar is the main product of slow pyrolysis. If the biochar must be returned to the soil, there is no product for the producers to sell for profit, except perhaps from the carbon market. However, if at an intermediate temperature, we can get nearly equal amount of bio-oil, pyrolysis gas, and biochar. And if we want, we can slightly change the proportions by adjusting the reaction temperature. Producers can thus sell gas and oil for profit, and the gas product, it can be sold as like a natural gas and is very expensive in China. And also, we can return biochar into soil, can maybe profit from the carbon market. So our study focuses on China and the state-of-the-art biomass intermediate pyrolysis polygeneration, BIPP for short, system as a near-term alternative to biogas until the latter becomes more cost-effective and feasible. So this is the system diagram of a demonstration BIPP system that we built. The biomass is first preheated to reduce water content and then pyrolyzed in a specially designed furnace with a continuous feeding system, which has about 10 times larger capacity than former pilot systems can do. The term polygeneration refers to multiple outputs, which in current case refer to pyrolysis reactor coupled with a heat recovery system and a micro generator to burn 80% of gas product to generate electricity, as well as storage and distribution system to supply the remaining 20% of gas for household use. The normal heating value of pyrolysis gas in this system is more than 10 megajoule per square meter. It is higher than the minimum required by Chinese national standard requirement for fuel gas for residents. So it can be sold as cooking gas. And then there are also liquid products, bio-oil and bio-acid. And 35% of product is biochar, which is a big deal. So this is the sorry, demonstration plant near Wuhan, Hubei, China, which is funded by the Natural Science Fund. It has continually run for 4 years and provided gas for cooking for 3,000 families around it. We will try to answer these 3 questions. Can it be profitable? How much carbon dioxide can be sequestered? What is the national emission reduction potential? To do so, we first have to model the system. Then, based on data get from the system modeling and data from experiments and demonstration plants, we can proceed with life cycle analysis. Finally, by collecting national data of biomass distribution and prices, we evaluated the national emission reduction potentials to modeling so the modeling is the foundation. The Aspen Plus simulator, a good simulator for chemical engineering processes, is used for modeling. A classic pyrolysis kinetic equation is used, and more than 20 reaction and secondary reactions are also included. And also the simulation results have been validated by experimental data. Our first question is, could it be profitable? Based on the model, we can get distribution of products and different temperature and capacity, and the system economic benefits depend on the incomes that are from the sale of products, meaning pyrolysis gas, electricity, and bio-oils, and potentially income from carbon trading market. Subtracting capital investments and other costs of the system, we can calculate the NPV, the net present value of the system. And we found among all factors influencing the NPV, capacity, and temperature had the greatest effect. Thus, we can draw a picture of two-factor sensitivity analysis of net present value. It is obvious that this BIPP system produced the most value at a temperature above 550 Celsius and biomass input above 610 per hour. Then we try to answer the second question, how much negative carbon emission can be realized? First, we draw the carbon flow diagram of the system. Carbon dioxide is first withdrawn from air and fixed into crops through photosynthesis after a series of processes, from crop connection, transportation, thermal conversion, to final use. Owning biochar is returned back to soil as a carbon sink. However, all these processes involve extra greenhouse gas emission. For example, the greenhouse gas emission from truck engines in transportation of the biomass. And we define these greenhouse gas emission as a life cycle greenhouse gas emission of the BIPP system. And we define the stable carbon in biochar as carbon fixation. And note that not all the carbon in biochar can last 100 years as solid carbon in the soil. As we mentioned before, only a part of it, and we measure it by stability. And after biochar is returned to soil, it is believed that biochar additions are also beneficial in terms of reductions in soil emissions of nitrous oxide and methane. These are also greenhouse gases. And this mechanism is very complicated with high uncertainty, but the carbon fixation plus this reduced soil methane and nitrous oxide are the greenhouse gas sinks. So then if these two sinks are subtracted from life cycle greenhouse gas emission, we can get the net life cycle greenhouse gas emissions, which can be a negative value. And then if we add the reduced here, see, and then if we reduce if we add the reduced greenhouse gas caused by bio-oil and pyrolysis gas sold to replace the fossil fuels, we can get the final total greenhouse gas reduction here. So the actual calculation of greenhouse gas emission involves many variables. For the demonstration plant, the specific results are shown in this picture. The left figure presents the life cycle emission carbon fixation by returning bio-oil into soil. biochar into soil, and also influenced by the stability of biochar, and also the reduced emission by biochar amended soil. The right figure represents the net life cycle greenhouse gas emission for the whole system. We found that the pyrolysis system will always be negative, usually from about like minus 60 gram to minus 12 gram carbon dioxide per megajoule it produced. And at the temperature above a little above 500 Celsius to 650 Celsius, and adding reduction by offset fossil fuels, the total greenhouse gas emission reduction could reach 166.45 gram carbon dioxide equivalent per megajoule produced. And then for our stat question, we ask what could be the emission reduction if this technology is applied all over the country? First, we investigate the crop residues application status in China. We find that 11% is used as household fuel, which could be replaced with cleaner biofuels produced by our system. And 22% are directly burned in open air, which is wasted. And other crop residues are used as fertilizer, animal food, and raw materials. So in our base scenario, we assume the crop residue used as a fuel 11% and burned in the field 22%. Together, 33% of all crop residues are available for our BIPP system. And to ensure that this study can estimate comprehensively the reduction in national greenhouse gas emission, 8 typical agriculture residues in China have been considered. Different biochar from different agriculture residues have various carbon stability in a 100-year time span. The stability of biochar is a critical factor, and in previous study, the oxygen to carbon ratio of the biochar has been proposed as an indicator and defining the threshold for biochar stability. So the lower it is, the more stable the biochar is. So in order to implore the differences of carbon fixation by biochar, and so we take experiment for various different.
我没有听明白你的意思，请再说一遍好吗？
Sorry. So for these various biomass feedstock and the oxygen to carbon ratio of the biochar products are tested, then we can predict the stability of the biochar from different crops. And also considering the different crops and crop years and soil type in different provinces in China, the greenhouse gas emission reduction in every province can be assessed. These results clearly indicate that some provinces rich in biomass resource could have a significant potential for greenhouse gas emission reduction. And the BIPP deployment can have a particularly important influence for Central East China, which is responsible for globally high greenhouse gas emission. And the economic indicator of NPV for BIPP has been studied as a function of different provincial biomass. It is found that the selling price of the crop residues plays a significant role in economic performance. For example, a BIPP in Henan has a poor NPV because the relatively higher price of wheat and rice crops. Also, there's abundant biomass resource. So as a result, and provinces such as Shandong, Hebei, and Qing could develop BIPP technology with strong economic feasibility. And we also evaluate the resulting reduction of air pollution by applying BIPP instead of open-air burning and domestic biomass burning in our base scenario. The results indicate a significant reduction in China's air pollution, including decreases in emissions of sulfur dioxide, nitrous oxide, NOx, for example, and the primary PM 2.5. And let's take PM 2.5 as an example. The BIPP could contribute to a reduction in annual emission by 1.76 megaton, equivalent to like about 20% of the total national primary PM emitted in 2014. And in addition, deployment BIPP could also even more pronounced effects regionally, especially in Shandong, Hebei, Henan provinces in North and East China, which are currently suffering severe air pollution. And to explore more possibilities, we designed more scenarios from future future from 2020 to 26 to 2030 and to 2050. And based on the recent status of biomass resource in China, and I have to mention that China did not pledge carbon neutrality when we submitted our paper, so we only considered 2050 but not 2060. And these scenarios assume greater and greater amounts of biomass used. Scenario 1 and Scenario 5 are two or not scenarios. Scenario 1 is for zero BIPP or Biochar, and we assume Biochar mature after 2030. And Scenario 5 is all BIPP, no Biochar. And then Scenario 2, 3, 4, and Scenario 6, 7 assume BIPP applied from 2020 to 2030, and then BIPP and Biochar are coordinately developed after 2030. And this is the result. The solid line is for the moderate scenarios, while the dashed line is for maximum scenarios. The blue line is BCCS only. The deep red line is BIPP only. And we can see before 2030, the blue line, Biochar only, it is in the bottom. And the cumulative greenhouse gas emission reduction increases with the growth in BIPP deployment. The more BIPP, more greenhouse gas reduction in near term. And after 2030, in the midterm from 2030 to 2050, the coordinated development of BIPP and BCCS scenario 2, 3, 4, 6, 7 shows larger reduction potential. This is mainly because if Biochar technology becomes mature, the carbon emission from pyrolysis gas burning in our BIPP system could also be captured. And in moderate scenarios, the BIPP coordinated with further BCCS deployment, the scenario 4 can reach up to like 8,620 megaton carbon dioxide equivalent reduction by 2050. And in a maximum scenario, the greenhouse reduction can reach 3,156 megaton and 21,803 megaton carbon dioxide by 2030 and by 2050, respectively. And in a national context, these options can reduce carbon emission per unit of 2005 GDP by 2% to 61%, which could contribute or approach or even almost achieve the emission target proposed in China's NDC, the National Determined Contribution for the Paris Agreement. And if we put this in a worldwide context, the Becker's global emission reduction target required to meet the Paris Agreement in the IPCC report is pledged at 28 to 65 gigaton. So China itself can achieve around like 17 to 31% of the global removal goal. And to sum up, the main finding of our study is we figure out a promising BIPP system that can be profitable at temperatures between 250 degrees to 650 degrees, and the BIPP do realize carbon negative emissions through biochar being returned to soil, and the development of this system should be any the better. Its national development could contribute both national carbon reduction goal and also the international negative emission target. And these are the limitations of our study. First, the static carbon intensity of various sectors were assumed. We just want to simplify the assessment. However, because of the national policy, the renewable energy policy, and the technological development, the carbon intensity for sectors should decrease gradually over time, and the decreased carbon intensity could lower the carbon emission for the upstream production and services over the whole life cycle of our system. So will cause a decrease in the greenhouse gas emission for the targeted system here. And the second, this study, we focus on biochar application only from the agricultural biomass and in some scenarios, the forest residues and energy crops. However, also we have other wastes, for example, the municipal solid waste could also be supplied as a significant source for biomass for pyrolysis. So, but we do not consider in this study. And the third, the agricultural production in the future has a high degree of uncertainty influenced by future population, climate change, and so on. And China projects that there will be no significant changes in agricultural resources in near future. So therefore, in this study, we assume conservatively that China's agricultural resource and residues would remain at the same level as presented in the present situation in the first half of the century, and we did not consider the improved crop productivity after biochar returning into soil. So future study will also involve the water consumption, considering the water retention effects by biochar in soil, and also water resource constraints. And finally, I would like to thank all the authors, especially He Wen, my student, always hardworking and available, and also other authors from State Qing Laboratory of China, EU Institution of Clean and Renewable Energy, at Huazhong University of Science and Technology, and Harvard University, University of Penguria, and University of Edinburgh, and Utah State University, Peking University, and also Tsinghua University. And I appreciate their solid input, advices, and suggestions. And especially, I want to thank the corresponding author, my advisor, Professor Mike McRoy. And also, I would like to thank foundations from China. And last but important, I also want to thank other members of the Half China Project on Energy Economy and Environment for useful comments, suggestions, and also many other friends who support us, and especially Chris for help to sharing these slides. And thank you for all your attention. And I would like to answer any questions arise.
Hey, Qing, that was terrific. Very, very excellent presentation of a very complex topic. I think you made it very accessible. So let me see, how do we see people with questions putting their hands up? Mike, do you have a question?
I think it was an excellent presentation, and this is a very important piece of work, not just for China, but also for other developing countries. I think in particular, opportunities to apply the same kind of technology in India is a really important thing. I also think that the idea of being able to use not just agricultural waste, but also municipal waste is really, really intriguing. So thank you, Qing, for an excellent presentation.
My pleasure.
Prem, you love that topic that Mike just mentioned, municipal waste. Do you want to say anything? You gotta unmute.
Is it unmuted now?
Yes.
All right. First, I want to thank you, Yang Qing. This is wonderful to listen to you and to hear that China is working on things that I personally have been also trying to promote in India for at least the last 10 years. I'm not a scientist like you. I have been a journalist. I've done a little research on the side, but I am delighted to be associated with Chris and Mike just now, and I look forward to meeting you one day. I just 2, 3 very, very brief questions I want to ask you. I completely agree with you, and exactly the same route needs to be gone in India, with perhaps minor differences. First thing I wanted to ask you was, you said that in the optimum pyrolysis, you get about 35% biochar. And you said that returning this into the soil will of course will increase its productivity. There's no question. But can you do it that so much, 35% of crop residues? As you know, for every ton of rice, you get 1.5 tons of more or less of straw. And now 35% of that is a lot of biochar. So returning so much soil carbon every year into the soil, I don't know whether is that feasible, or in fact, would it be better to put a part of this into the soil, which I think is absolutely essential anyway, but the rest of it is used for the other purposes you mentioned earlier, which is producing, transport fuels. I'll just stop there. There are many questions. I'll send them to you in writing. I don't wish to take up more time than that.
Okay. For the first question, thank you for your question. Yeah, according to the ratio between the feedstock, the straw, the crop, and the grain, we can get a lot of crops, a lot of agricultural residues. And a short answer is, I'm not sure, but I think it is possible, because in the old days, people used to return all the all the straw back into the soil to remain the soil fertility and to keep the soil productivity.
May I comment? I read a study done by the European Union in which there was a long 60-year study of the Ukraine and with wheat straw. And in that, they found that actually after you cut the wheat, there's the roots and the bit of the straw, a few inches of straw left, that if that is plowed back into the soil, it is sufficient to maintain the carbon level in the soil. And then the next question is even more important for rice straw, is what do you do with the 10 or 12, or say about 30 centimeters of the stalk of the rice between the 10 or 15 centimeters left at the bottom, and then the grain, which of course is what is we are burning it today in India and absolutely suffocating ourselves. So I mean, I think there's more than one use that we can put the straw to. And the first one, I think, is, of course, plowing back the stubble. We call that what is left at the bottom of the stubble, and I'm sure you have a similar word for it. And then that still leaves you with a large amount of straw, which is at this moment just being burnt or being used for bedding for cattle and that kind of thing, or for mushroom beds in India, that kind of thing.
Oh, so it's just burned directly in the field?
Well, it's burnt directly in the field, and it's doing terrible damage to the fields because it hardens the top of the soil. It destroys all the microbes in the soil, and it also eliminates a whole lot of other micronutrients, metallic micronutrients. But the worst part of it is that hard soil on top, that hard layer, is leading to waterlogging in India in a very large way. We have to get out of this fast, and the government doesn't have a clue at the moment. And I think that what you're describing is just the way to go.
Yeah, that's really terrible. Actually, in China, about maybe 4 or several or maybe 5 years ago, we also banned a lot of the crops, the residues, directly in the field. Even now, I think some places in China also do these things. It's really bad for the soil. We have to stop this right now. I cannot agree with you anymore.
Anything I write on this, I will send to you. It will be my honor and pleasure.
Okay, let's get some other questions in. Jed Schwartz has had his hand up for a while.
Thanks. I was very interested in your presentation. I'm a little slow picking up what you were saying, so I was wondering if you could go back over a bit of it. My understanding, for example, and you should please correct my understanding or ratify it. It has to do with, you're saying that biochar, when injected into the soil, can increase the soil's fecundity. That is, its ability. It's like fertilizer. It makes the crops grow more. This is correct, yes?
Yes, it is correct.
So biochar comes from, now you're also talking about extracting CO2 from the atmosphere. Can that extracted CO2 be converted into biochar or used to enrich the soil? Or have you studied that at all?
Sorry, can I rephrase your question? You mean the biochar in the soil can also absorb the carbon dioxide in the atmosphere?
Yeah, is there any relationship? Is there any interchangeability between extracted CO2, which, I mean, at one point they were talking about burying extracted CO2 in the ocean floor. There was another idea that it might be sent into space or to the moon or to Mars. But that was my idea. I mean, not a very good idea, probably. But anyway, the question is, can you take, assuming that you can get CO2 out of the atmosphere, is there any way to get it into the soil or into the biochar category in such a way as to enrich the soil? Is that too off the wall a question?
Yeah. I gotta interject here. That's precisely what the process that Qing is talking about is doing.
That's what I thought.
It's taking crop waste, which have brought in carbon dioxide from the atmosphere, and turning that into biochar and introducing it into the soils. Mike, I think you had a follow-up to another question, and then Kathleen, we'll get to you next.
Yes, I did. So again, it's nice to see Prem as part of the audience here. And I don't know if people have seen this, but there's a story from Bloomberg today that is suggesting that India plans to go carbon negative 10 years earlier than China. I don't know if people have seen that particular story. So the idea that India is going to beat China by 10 years in terms of going to zero emissions is an astonishing proposal. But what I wanted to do is to ask Qing again about some of the other elements of the biological processes that she's talking about here. So, for example, we know that in order to grow crops, you have to not only have CO2 from the atmosphere for photosynthesis, you also have to have a source of water, but significantly, you also have to have sources of nitrogen and phosphate and other trace nutrients. And my question is, what actually happens to the trace nutrients, notably nitrogen and phosphate, in terms of the production of the char? In other words, are those elements conserved, or otherwise, do we have a problem of, in fact, losing productivity of the soil because of the depletion of these trace nutrients? So that's my question, Qing.
So thank you, Mike. So I'm not quite catch up your question. I'm not sure. So can you rephrase it for me?
Yeah, I mean, in order to preserve the productivity of the agricultural system, you normally have to apply fertilizer. Nitrogen, phosphate in particular, are key elements in the production of any crop. So when you go through this sequence of extracting the crop itself and then the crop waste and transforming the crop waste to biochar, as you're suggesting here, my question is, what's happening to the trace nutrients? Do you have to keep fertilizing the soil with nitrogen and phosphate in order to keep this process going? Or in fact, does the biochar in fact sequester a significant amount of the nitrogen and phosphate?
Okay, thank you. For this question, I think right now our study shows the fertilizer are still needed for the crop grow, and if we add biochar into the soil, and we can reduce a certain amount of fertilizer that should be used.
Okay, thank you.
You're welcome.
Kathleen Draper.
Hi, thanks very much. That was really, really interesting. First off, I would like to invite you to speak to the board of the International Biochar Initiative about this, because we've been very interested in what China is doing. I've been over there a few times to see the different pyrolysis setups there. But my question was on your assumptions in the carbon markets. Is it already accepted on a carbon market in China? I know it is in 2 small startups in Europe, and that Vera is developing a standard as well. But I'm curious about if it's available and what the pricing assumptions are.
There are like 7 or 9, I'm not quite sure, pilot carbon emission trading market in China, and Hubei province, Wuhan city, Hubei province, it is one of these pilot market. And right now, the price for carbon in Wuhan is about 40 RMB, 40 Chinese yuan, about maybe $8 per ton. So it's relatively very cheap. And right now, we only treat the carbon emission from the power sector. But in the future, more sector will be included according to the report from the government.
Thank you.
You're welcome.
Any other questions? Raise your hand. We're going to wrap up here quite soon. I will ask one question in the meanwhile. Qing, you didn't say very much about the kind of logistical challenges of the collection of the biomass and its transfer to the pyrolysis reactors, and then also the transfer of the biochar to the fields for distribution. Can you say something for the benefit of the audience about, what you actually modeled about those two steps?
Yeah, actually, the transportation, it is very important. And it will generate the greenhouse gas emission. And in this case, we assume an average distance from the crops to the plants and from the products to the soil. And we also do some sensitive analysis of the distances. And we can see how our results will be changed or influenced by the transportation distances.
Good, thank you.
Thank you.
Okay, I think we're sort of right on time, and thank you very much, Qing. People with questions, I'm sure Qing is happy to receive them at her email address. Is your email address on here somewhere? Maybe you can put it in the chat. Remind everybody that we have another talk on April 7th at the same time, same format. So Qing, let's give a big thank you to Yang Qing for her excellent talk.
Thank you. It's really my honor to do this, and I'm happy to answer any questions. This is my email. I type it to the chat. The chat. Yeah, there is.
We'll stay open for a little bit longer so people can get that address. qyoung@hust.edu.cn.
Yes.
Okay. Okay. Thanks again.
Thank you. It's my pleasure and my honor.
Bye, everybody.
Bye.